Hello, welcome back. In this video, we'll discuss the direct and indirect band semiconductors. We have seen in our discussion about a particle moving through periodic potentials that energy bands are possible. But when you represent the energy bands in the K space, we'll get curves something like this. The lower curve represents the valence band and the upper curve represents the conduction band. If you look at the bottom of the conduction band, this is the conduction band and this is the valence band. Again here this is the conduction band and here we have the valence band. Along the x direction we have the K, that is the wave vector, and along the y direction we have the energy. When you look at the direct band gap semiconductors, you notice that the bottom of the conduction band and the maximum value for the valency band, they are aligned for the same value of K. In this case maybe it is 0, and the energy gap we define as the difference between the bottom of the conduction band and the top of the valency band. This difference is called as energy gap, and in the conduction band we'll have generally the electrons and in the valency band we have the holes. Any recombination of the electrons with the holes will occur directly without the mediation of K. Means K vector is not involved in the recombination process. Such semiconducting materials are called as direct band gap semiconductors. On the other hand, if the bottom of the conduction band corresponds to a value of K, say K prime, and the top of the valency band corresponds to a value of K, let us say K0, the energy gap is the difference between the bottom of the conduction band and the top of the valence band. This is the energy gap. So in these two cases, perhaps the energy gap is almost same. However, for an electron to recombine with the hole in the valency band, certain amount of K is needed, because the electron would come something like in this direction, whereas it has to recombine with a hole that is available with a different K value. A different K value means different momentum, because momentum P is equal to h bar K, where h bar is the Planck's constant, h divided by 2 pi. That is how momentum is connected to the wave vector K. These type of semiconductors are called as indirect band gap semiconductors. The example for an indirect band gap semiconductor is silicon, and the example for a direct band gap semiconductor is gallium arsenide. In this video we have seen what are direct band gap semiconductors and what are indirect band gap semiconductors. The semiconductors can be divided into two groups basing on the band gap. One group is direct band gap semiconductors, the other group is indirect band gap semiconductors. In the case of direct band gap semiconductors, the bottom of the conduction band and the top of the valency band, they will be aligned along the same vertical corresponding to one particular value of the K. Whereas in the case of indirect band gap semiconductors, the bottom of the conduction band and the top of the valency band, they are not aligned along the same vertical corresponding to one particular value of K. Rather, the bottom of the conduction band will occur for some value of K and the top of the valency band occurs at a different value of K. And any recombination in this type of materials, that is the indirect band gap semiconductors, involves momentum, and the recombinations will release both light and heat. In the case of direct band gap semiconductors, a recombination happens without the mediation of K vector. One example for the direct band gap semiconductors is gallium arsenide, and an example for the indirect band gap semiconductors is silicon. Thank you.